In this video, we'll be looking at precipitation, acid-base, and redox reactions. Precipitation reactions occur whenever you have mostly a double replacement reaction that's going to form a solid as one of its products. In this case, if we look at the reaction, it says how many grams of precipitate are formed from a reaction between 25 milliliters of a 0.1 molar calcium nitrate solution and 10 milliliters of a 0.1 molar sodium phosphate solution. Looking at this, we can see both of our reactants listed out here. We've got our calcium nitrate and our sodium phosphate, and it says those are the ones that are reacting together. And so we can go ahead and write our chemical equation. That's almost always where we're going to start whenever we're doing one of these problems. So we're going to have our calcium nitrate, so we're supposed to be a 2 there, plus sodium phosphate as our reactants, and then we're going to go in and add our products also. It doesn't in this reaction specifically tell us what either of our products are going to be, and so we need to figure that out. We do see that this follows the pattern of a double replacement reaction, which means we're going to switch the cations. That means that our sodium and nitrate are going to be paired up together in 1, and both of them have a 1 charge. Sodium is +1 and nitrate is -1. So that's pretty straightforward. It's just NaNO3. Our other product is going to have calcium and phosphate. Calcium has a +2 charge, phosphate has a -3 charge, which means that our final product should be Ca3PO4, 2, the 2 coming from the charge on the calcium and the 3 coming from the charge on the phosphate. After this, we need to go ahead and balance it. To balance this, we need to look at each atom individually. First thing we can notice is the calcium needs a 3 in front of the calcium nitrate to have that balanced. And that gives us 6 nitrate ions. And so we need to put a 6 here in front of the sodium nitrate. After we add the 6 there, that gives us 6 sodiums, which means we need to add a 2 in front of the sodium phosphate, which also balances the phosphate ion because now we have 2 of those on each side. And so this entire thing can be balanced by considering the entire polyatomic anion as one whole, because we see the nitrate and the phosphate are identical on each side. There's no real changes. We don't have any nitrites turning into nitrates or anything like that. Once we have this, it's not required for this problem, but we could write a net ionic equation. And to do that, first we would need to write a complete ionic equation and look at what all ions we actually have in the problem. In order to be able to write a complete ionic equation, we need to know phases, which is also important for this problem because this problem refers to the precipitate. The precipitate is the solid that's formed at the end of this problem, and so we're going to need to know what that is. Our solubility rules tell us that anything with an alkali metal, like these two right here that have sodium, is going to be soluble in water. So we would add a little AQ there beside that. It also tells us that nitrates are soluble. Here, in this case, we know we have a precipitate, so even without having to look at any of our other rules, we can tell that this calcium phosphate is going to be the solid because of a couple rules we do know, which is about the nitrates and the sodium. And so that tells us that we're going to have our solid calcium phosphate. After we do this, to write our complete ionic equation, we're going to take each of the aqueous substances and we're going to break it into its ions. So we're going to have our cation, which for this first one will be Ca2+, and our anion, which would be NO3-. And we're going to do this for each of our aqueous substances. The only one we should leave together is the calcium phosphate because that one's a solid. Solids do not dissociate in water, which means that we're going to have the entire calcium phosphate molecule, or not molecule, the entire formula for that left together because the compound is going to just stay as one whole piece. Okay, so looking at this right here, we are missing some charges, so let's go ahead and add those. Everything that I split into an ion is supposed to be aqueous, so I'm going to write those in. and then I'm just going to put my little solid here by the calcium phosphate. from this, we can write a net ionic equation. And to do that, we're going to take everything that we see identical on each side of the problem and cancel it out. Those are our spectator ions. In this case, we see an identical NO3- on each side, so those can go away. We also see an Na+ ion on each side, and those can be canceled out. The only thing we should have as a product in this reaction should be our precipitate, so Ca3PO42. And then our reactants should be the two things that go together to make it. So our Ca2+ and our PO4 3-. And those come together to make our products. Now, for this specific problem, it wasn't asking us to do that, and so that was just a little bit of extra information on what we could have to do in these problems. But one thing we can notice is that our problem actually gives us information about calcium nitrate and sodium phosphate. Both of those in our complete ionic equation got split up, and then half of the ions got canceled out whenever we did our net ionic equation. So the most convenient equation for us to use here would be the first one. So I'm just going to go ahead and get rid of this information, because we don't really need it. So looking back at this problem, let's go ahead and set up what we're going to be doing. Since I'm given information about both of the reactants, and I'm looking for information about one of the products, this is a limiting reactant problem. Anytime we see that pattern where we're given information about both reactants and asked about the products, that's the type of reaction we should be thinking about. So what we're going to do, I'm going to find the number of moles of each reactant and then do a separate stoichiometry problem to figure out how many grams of the precipitate can be made from each of the amounts of reactant. So the first thing I'm going to do is I'm going to take care of the calcium nitrate, and then we're going to follow the same pattern for the sodium phosphate. To find the number of moles given the volume and the molarity, the first thing I need to do is take this 25 milliliters and turn it into liters. And to do that, I just divide by 1,000. So I'm going to get 0.025250. Excuse me, it's having a little bit of technical difficulties. That's how many liters of my first solution I have. I'm going to do the same thing with my 10 milliliters. That becomes 0.0100 liters. Now that I've got both of those, I can use my molarity equation. And that says that molarity is equal to moles over liters, which can be rearranged so that moles is equal to molarity times liters, which is going to be the most convenient equation for us to use here because we have liters and we've got molarity and we want to find the number of moles so we can do some stoichiometry. So what we're going to do for the calcium nitrate is we're going to take 0.0250 liters and we're going to multiply it by the molarity of the calcium nitrate. And that's going to give us our molarity, or our number of moles. In this case, it's going to be 0.00250 moles of calcium nitrate. And it's okay that we have a small number here. It's going to end up working out in the end because we have a very small volume and our molarity is not really that big. It makes sense that our number of moles would be small also. And I'm just going to do that same thing with the Na3PO4. I'm going to take the 0.0100 liters. I'm going to multiply it by the molarity, which is 0.100 molar. And I'm going to get my number of moles, which is 0.00100 moles of Na3PO4. So now that I've got that, I know exactly how many moles of each of my reactants I have, which is going to be important. So I'm just going to take this and move it on over here so we can have a little bit more room to work with. Okay, so I'm just going to put this right over here. Nope, I had some stuff pop back up there. I'm not sure why that came back, but we're just going to go ahead and get rid of this. Alright, so next thing we're going to do, since I've got moles of each of my reactants, I'm going to figure out how many moles of my product I can make from that. And I can turn that into grams using one more fraction for a stoichiometry problem. I'm going to make two separate equations for this. One for the calcium nitrate, one for the sodium phosphate. So I'm going to take my 0.00250 moles of calcium nitrate, and I'm going to multiply that by two fractions. My first fraction should have the number of moles of calcium nitrate and the number of moles of calcium phosphate, because that's my precipitate. That's what I'm trying to figure out the information about. In my balanced equation, my coefficient for the calcium nitrate was 3, so that's what I'm going to put here as my number of moles. Calcium phosphate had a 1 for the coefficient, so that's what I'm going to put instead. And then my second fraction should have on the bottom 1 mole, and on the top the molar mass of calcium phosphate. Which is right about 310.17 grams. So now that I've got all of this information, what I need to do is type this in my calculator and find my answer. And whenever I do that, I get 0.258 grams of calcium phosphate. That doesn't mean that's my answer, that's just one. So my answer here should be 0.258 grams of Ca3PO4, 2. And then I can do the same thing for the sodium phosphate. So it says, according to this problem over here, that I have 0.00100 moles of Na3PO4. I'm going to set up my two fractions. On the bottom of the first one, I'm going to have 2 moles of Na3PO4. And on the top, I'm still looking for information about my precipitate, so it's still 1 mole of Ca3PO4, 2. Same thing on the bottom, 1 mole of Ca3PO4, 2. And on top, I'm going to have 310.17 grams of Ca3PO4, 2. And whenever I do the math for that, I should be able to get my answer, which is 0.155. Once again, that's my second possible answer. To decide which one of these is the correct answer, since this is a limiting reactant problem, it's going to be whichever one of these is smallest. And that would mean my correct answer would be my 0.155 grams of calcium phosphate. That's how much precipitate I'm actually going to produce in this reaction.